In this video, we are going to introduce encryption algorithms and give a couple of simple examples or examples of simple algorithms. But first, a bit more of a terminology. The original form of a message is known as plain text, as you rightly know, and the encrypted form is called ciphertext. So for convenience, we denote a plain text message, P, as a sequence of individual characters, P1 to Pn. Similarly, ciphertext is written as C is the set of C1 to Cm. Note here that the M and N might not be equal, since we don't know what the hash function will do, or the crypto function will do. Now, for instance, the plain text message hello world there would be denoted as the message string HELLO space WORLD. And it can be transferred into the ciphertext C1 2 to 14 or whatever M will be. And the encryption algorithms tells us how the transformation is done. We use this formal notation to describe the transformations between plain text and ciphertext. For example, we write C equals E of P and P equals D of C, where C represents the ciphertext, E is the encryption rule, P is the plain text, and D is the decryption rule. What we seek is a crypto system for which P equals D of E of P again. In other words, we want to be able to convert the message to protect it from an intruder, but we also want to be able to get the original message back so that the receiver can read it properly. So encryption algorithms are crypto systems, or a set of rules to translate from plain text to ciphertext and back. But instead of everyone having their own encryption algorithm, we can use each other's and standard ones with a key denoted by K here. So the formulation becomes the ciphertext equals the encryption of P with K. Now, encryption algorithms can therefore be compared to physical locks. It would be really expensive for you to have someone invent and make a lock just for your house. Also, you would not know whether a particular lock, or this inventor's lock, was really good, or how it compared with other locks. A better solution is to have a few well-known, well-respected companies make standard locks that only differ according to the physical key. Then you and your neighbor might have the same model of lock, but your key will open only your lock. In the same way, it is useful to have a few well-examined encryption algorithms that everyone could use, but the differing keys would prevent someone from breaking into what you are trying to protect. There are two types of encryption algorithms, symmetric and asymmetric. The symmetric one has the same key to encrypt and decrypt. So K is the same there. There are mirror images, so the decryption and encryption are mirror images. And the asymmetric one has different keys for encrypting and decrypting. So KD is not the same as KE. Although KE inverts KD, but they're not the same, and preferably can't be you can't find out what KE is from knowing KD, and vice versa. Now here's a picture to explain the difference. So symmetric one at the top, asymmetric at the bottom. So let's take a look at some simple examples of encryption algorithms. These will only be symmetric ones. To understand encryption algorithms, we have to take a look at representations. So if you think about just the simplest form of a message written in the standard 26-letter English alphabet, the convention on paper when you're writing it out is to write the plain text in uppercase letters and the ciphertext in lowercase letters, like in that example below. So we're going to treat encryption algorithms really simply and superficially. They're based on mathematical transformations and can be explained far more accurately in mathematical form. So don't overthink these examples, and don't assume that these examples are the only way to do this. These are the simplest forms of encryption algorithms. Now, with the representation in mind, consider the simplest, even like the simplest of the simplest encryption algorithms, basically doing arithmetic transformations on the letters, such as A plus 3 equals D, or K minus 1 equals J, and so on and so forth. And we have to think about the alphabetical table as a circle. So if you do Z plus 1, you get an A. With this kind of representation, we have two simple forms of encryptions. Substitution, where we just exchange one letter for another, and transpositions, where we just shuffle the letters or rearrange them. The simplest form of substitution is the Caesar cipher, where we've just shifted the characters by a set key. And the key is just how many characters you shifted by. It's really easy to memorize and implement, but it's that much easier to break. So you see, going from here to there, so T, BW, T, 1, 2, 3, or TW. So you see in this example what the Caesar cipher is. As I said, the simplest form of substitution. And should never be used in, probably not necessary to tell you this, but it should never be used in production. Now, while Caesar cipher is a uniform substitution, that is, the same rule applies to every character, there are other forms as well. We can describe substitutions mathematically as permutations, and they're just a set of rules. For example, these are two permutations of the 10 first numbers. In the first example, pi of 3 equals 5. So pi of 3 equals 5. Letter in the position, that is, the letter in the position 3 is to be replaced by the fifth letter. C is transformed to E, right? Now, I'll leave it up to you as an exercise to figure out what the actual function is for pi 1 and pi 2. I'll give you a hint that pi 2 is far simpler. It is a uniform permutation, but pi 1 is a set of rules with if statements. So there might be a different rule that applies to this part than this part and that part. Or that part. Another way to substitute is to use a key using a word that controls the permutation. So for example, if we could use the key word such that W, O, R, and D substitute for the first letters of the alphabet, then we fill the remaining letters of the alphabet in the order that they came. So we see A, B, C, but D has already been used, so we skip to E, F, G, and so on, and so forth. But we can also use less regular rearrangements, for example, where we cyclically choose every third letter. So instead of going A, B, something, was it A, D, G, J, and so on. And when we get to W, Z, and then we go third C, F, I, and so on. Now, these examples that I've covered are really, really simple encryption algorithms. As I said, they should never be used in production. They could be made a bit stronger with longer words for keys or more complex rearrangements, but they're still really easily breakable and should never go into production.